Glycine is the simplest amino acid out there. If you imagine the generic amino acid structure, you've got the amine group, you've got the carboxylic acid group. If you got the carbon that's in the middle, you've got the H that comes off of it anyway, and then you've got the R group, which can be a variable group. It can be anything that it really wants to be. Replace that R with a single hydrogen and you have glycine. The simplest amino acid, the chemical formula, probably something like C2H1, 2, 3, 4, 5, 6, C2H6O2N, just one N. So while it is the simplest amino acid, it still has somewhat of a complicated chemical structure. But when you look at a molecule of glycine compared to some of the metabolites that are needed to produce energy, it doesn't actually seem to be one of the ones that can be catabolically broken down into the thing. Glycine contains 2 carbons, acetyl-CoA contains 2 carbons, so it would have to be on an equivalent scale going off of carbon chain units to actually get into acetyl-CoA. But in terms of how glycine can be metabolized, that's not how glycine metabolism works. Glycine is not metabolized into acetyl-CoA, it is metabolized into pyruvate. Pyruvate has 3 carbons inside of its chemical structure, and that means that glycine actually has to be built up to end up making pyruvate. But glycine is actually a very, very useful molecule. Despite it being a non-essential amino acid, we still need lots and lots of it inside of our diet because it can be pretty difficult to produce for our body. Our body can produce glycine from other amino acids such as threonine, but glycine in itself is one of the major components inside of collagen, which is the big polypeptide that makes up like some of your skin. It's like the layer under your skin that is made up of collagen, which is a long protein. You've got things like keratin, which probably are less so glycine, but again, it will contain all this stuff, and so will loads and loads of hormones and loads of enzymes. They'll all contain glycine because it is the simplest amino acid, probably the most common and henceforth the most important. But how does your body metabolize it into energy? While it has its various uses in other areas of the human anatomy, how can your body utilize it for energy if it so needs to? While glycine is actually the least efficient amino acid at producing energy, if you took a gram of glycine, it would only end up contributing to around 2-ish calories, while proteins contribute to 4 calories a gram on average. Because glycine is the most simple, and you actually need 2 glycines to end up being able to utilize it into energy, this means that it ends up having a very, very low calorific yield and has the calorific yield of 2.34, something in the region of that. So to start with the metabolism of glycine, you take a molecule of glycine, you add it to a big, massive protein complex, which is made up of an H protein, a T protein, a P protein, and an L protein. You will combine the glycine with the H protein, and this means that you add glycine to the end chain, the end bit of this specific protein. You will end up having CO2 on the side, so you're only really left with the sort of left side of the molecule that contains 1 carbon and the amine group, as well as a couple of hydrogens as well. That'll be attached onto this sort of protein complex. This reaction was catalyzed by the enzyme glycine decarboxylase, and I'm pretty sure this will catalyze a few of the other reactions as well. Now, in the second step of glycine's metabolism, you take a tetrahydrofolate molecule completely separate. You will add it to the H compound, the H protein that I talked about earlier. This will end up turning into methylene THF, which stands for tetrahydrofolate, plus the other part of the H protein, as well as an ammonium ion. So this means that the H protein is somewhat back to normal. This reaction is catalyzed by the enzyme aminomethyltransferase because it transfers an amino and turns it into ammonia, as well as transferring a methyl group as well, hence why it becomes methylene THF instead of just straight up THF. The H protein that ends up being left on the side of this reaction will then be reduced by NAD and NADH and go through a separate reaction, which means that the H protein can return to how the H protein was when it received the glycine in the step 1 reaction. This is actually a cyclic sort of cycle, known as, which is one of the ways that glycine can be metabolized. Now, if you are still watching, you're probably going to be incredibly confused with what these large, massive molecules have to do with goddamn glycine, the simplest amino acid out there. But in the next step, you will see how 2 glycine molecules are actually used to produce 1 pyruvate. Glycine is one of the reactants inside of this reaction. Glycine plus 5,10 methylene THF that has been produced inside of the many reactions that we've talked about just now. This will then turn into serine, another amino acid, plus H4 folate. This reaction is catalyzed by the enzyme serine hydroxymethyltransferase. This enzyme is reliant on PLP, pyridoxal phosphate, to actually carry out its mechanism. Now you have serine, another amino acid. This amino acid can then go through a 1/2-ish reaction step to end up forming pyruvate. Now, while the next and final reaction is catalyzed by one enzyme, it almost happens in like 2 parts. The enzyme is known as serine dehydratase, again a pyridoxal phosphate reliant enzyme, and it seems that serine, the pyridoxal phosphate initially, will get rid of a water molecule, and then the next phase of the reaction can occur where an H2O molecule will be added to get rid of an ammonium ion. This will end up forming pyruvate. Pyruvate can then end up going into its various functions in the body, including energy production. But with that, that's about all I have on glycine metabolism, and I recommend subscribing because I like this community of young tribal people who are willing to improve themselves so much more than they already have, and good luck.